Okay, good. Good morning. Nice to see you. It's getting less and less every lecture. I'm used to that. It's getting more and more online. I'm also used to that. But today is an important lecture, I believe, because it's the first, what I would call a real machine learning algorithm. Today we talk about linear regression, which is truly an automatic approach to find a generic solution to almost whatever problem, computational problem you have. Before we get to that, I want to get back, I think last lecture or even in the first lecture, we talked, I think one student of you asked a question about LLMs, so things like ChatGPT, is it supervised or unsupervised? I believe I told you it's kind of unsupervised. And I told you, but it's complicated, and this is just one example of a discussion on Twitter, on X, with it attracted at least, how many, about 75 comments, a discussion about are LLMs supervised or unsupervised learning. So it's, you can debate for either side. I just want to make you aware of that. It's not important for this lecture, but all right. Let's get back to the last lecture, just the examples we stopped talking about last time. We had this example with the students who spent a certain amount of time, have a certain average marks in their studies, and then get a certain salary after they graduate. And we wanted to predict for a new student the salary based on the numbers we have. I told you it's always a good idea to plot the data. To make it simple, we ignored some of the columns and had it two-dimensional. It was important to note that we had the independent variable, the attributes, so the average marks on the x-axis, and we also had the label included in the chart. Remember, last lecture we talked about K and N. In K and N, we did not have the label included on any axis. The label was just encoded as a symbol in the vector space. So in linear regression, the label is included in the vector space. And this is the very first example from the first lecture where I told you already it would be nice to have a function where you can just input your data, treat it as a mathematical function, output, like calculate something and directly output the prediction. So right now we are interested in this one here. If you only look at this input, the average marks, it would be a function f of x equals y. We want to input 2.0 and output y here. So we are looking to automatically, and that's the big point here, automatically find a function, a linear function in this example, that models somehow the existing data as good as possible. So that f of 1, that would be here, would be roughly 58,000. F of 3.7 would be 36,000. And then again, the big questions, f of 2, what would that be? We talked about this already, and I told you need to learn this. It's important for the notation to understand this. Tabular data as a matrix. So we have, this is the data set that you normally download from the internet, that you have in your company, that you work in the lab sessions. It's the data set D. Each entity, each entry in the data set corresponds to a cell in your table. So that could be like this, what is it, the row ID, that could be the student ID, that could be the average marks. And then typically, and this is important, typically the last column is the label, but not necessarily. You can use anything in your data set to predict. You could equally well, so we have now always the example of predicting the salary, but you could equally well try to predict the average marks based on the time spent and the salary the student gets, assuming you have the data. So again, it's just like a habit, or it's typically done that the label is the last column, but not necessarily. And then you split up your data set into the matrix X and the vector Y. X are all the independent variables, the attributes, so your student data, and then you have typically one vector that, or yeah, one column table that includes all the labels. So this label is the label for this student, this label is the label for that student, and so on. And you can also write each instance, each student, so this part here, as a vector. That's this one, so it's the same. I think I made that here. One moment. So that's the data set, the attributes here. That's the same. You have here the labels. And just to make this clear, that's the same, the blue part. So this instance X1 is the student, the first student in your data set with these attributes. And sometimes we look at the transposed data because later we want to multiply matrices. But that should be relatively easy and to understand later. So sometimes this is just written like this. So keep in mind, if you see something like this, when it's transposed, this is again one instance in your data set. Let's look at an even more simple example and look at the goal of linear regression and basically any regression and machine learning algorithm. Given is always a few samples of data. In this example, just a single attribute, X1. So I don't know why my laptop is making noises all the time. Sure. So a single attribute, X1, and one label. You can write it as the matrix X consisting of those vectors. That's the same. This writing notation is the same as here. And then we want to predict for any given X1, can be any real value. We want to predict for any X1 the corresponding Y. And here we plot the data. So we see already that probably what we want looks roughly like this. And we call that the hypothesis, the linear model or the hypothesis. In theory, you could always find a perfect model that models all your existing data points. Now, whatever, as long as you don't have two different points, like as long as you don't have two X, which are identical with different Ys, you can always find the function that models all data points. It could be like this, then the function. If your data points are widely spread, you could still find a function like that. In this case, you have 4 data points, and with a polynomial function of the 5th degree, you could find a perfect model. So this function, if you somehow came up with a way of finding this function, it would allow you to calculate all these points perfectly, the given data. So for x1 equals 1, you just plug the 1 in here to the x, here, 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 and here. And you will end up with 2.5. And that's exactly what we are looking for. For the input of 1, the output would be 2.5. And the same is true for the other values. And then if you want to make a prediction, so once you have this function based on the given data, you can easily calculate or make predictions for any new data. So if you have something, an entity with an x1 value of 3, you can put the 3 into your function, as that's the input, and you end up with this point. It's okay. I know what the problem is. The screen is off now, and that is because my battery pack is empty. But I will find a solution for that. I hope. Yes, I will. see. By the way, this is a pretty cool tool. It's wireless HDMI. As long as you have electricity, this works really nicely most of the time. It's just a bit slow in the beginning. Yeah. I just tap here and now it should. Well, okay. Good. All right. That's the point. Yeah. So with a single input variable in your data set, with just one attribute in your data set, we need a function that has two variables, a straight line. A straight line is defined by mx plus b. So we have two variables, m and b. No. Once we have found m and b, we have our linear model and we can make predictions. But this is an optimization problem because there's an infinitive number of possible m and b's because they are both real numbers. So we need to find solutions. Two possible solutions out of the many are, for instance, this function. If we somehow came up with a way to find this function, we could make predictions. So this would be our model, our hypothesis. And for the given points where we know already the right answer, we would make these predictions, the yellow dots, which are, as you see, not perfect. They're all quite far off. Now, if we were to find another model like this, so our hypothesis now would be 2.6 plus x1, that looks better already. Then for the given points where we know already the right answers, we would come up with these predictions with this, 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 and this. If we want to quantify how good this works, we would just measure the difference between the true data, the true label, where we know this is the right answer. That's the actual salary that the student really got, and our predicted salary, which we abbreviate as y hat. So remember that the real label is y and the predicted label is y hat. And the difference between that is the error or the residual, which is just the difference between the two. And of course, the lower and then we sum up all the errors. Our goal is typically to have the lowest average error. And we want to minimize the error. So a bit more formally, we want for each instance xi in the data set to predict the corresponding label yi as good as possible. Because the underlying assumption is if you can predict the existing data well, then it will work well as well for new unseen data. So we need to find a function that is mapping x to y. A different way of writing this, or sometimes you will see these notations. So we have this function, you could also call it an algorithm, but now we need to find another algorithm that's actually linear regression that gives us this model, this function. So based on our data set that we have, we want to input that into our linear regression algorithm. And this linear regression algorithm should then output our hypothesis or the model or the function. And I'm really sorry for all these different words. I'm using all of them so that you get used to them, because I don't know, if you look some videos online or read a book, they will use one of these terms. Yeah, just some more notation. As I mentioned before, there's an infinitive number of possible models. So the hypothesis that we want to find is an element of the hypothesis space, and this is infinitively large. Okay. How would you do it? It's your task. Your boss tells you, wow, I have this great idea. We need something to automatically find a linear function for this given data. There's all these possible solutions. Now it's your task to come up with an algorithm that is finding the optimal linear model. And not just for this particular example, but that works for any type of, for now, one-dimensional data. I mean, some of you know the solution already, probably because you attended the other lectures or something. But if you have, if you have never heard of this or thought of this, do you have any ideas? Yeah.
Also ich würde jetzt vielleicht so vorgehen, dass jetzt nicht unbedingt genau alle Punkte durchgeht, dass sie auch überall durchgehen, sondern gucken, dass sie vielleicht so in der Nähe von so vielen Punkten wie möglich ist, aber jetzt nicht alle genau jetzt durchgehen, dass man sagen kann, es kann mal sein, dass man mal Ausreißer hat oder sowas nicht.
Yes. And how would you do that exactly? Can you tell me like a few steps? First, do this, then do that. Think of an algorithm. So the idea sounds, yeah, plausible, but how exactly would you do that? Yeah.
I write a general function like this.
What do you mean like this?
Yes. In X plus B.
Okay.
And then I write for all the points that the print have, for the data points that the print have. I would write the sum of the square root of the write y1 minus mx1 plus b plus y squared plus y2 minus mx2 plus b squared plus all the points. Then find the minimum.
How would you find a minimum of what? Of the errors?
I think if I multiply all of those, I will get other function in x and b. Sorry, in m and b. And maybe I can do.
Okay. That sounds like the right direction. Have you ever heard of linear regression before?
Once I did.
Yeah. Because if not, that would be very, very clever to come up with this idea, to take the squared error. You will see that this is probably the right answer that you mentioned. You square the errors later, and then you take the gradient, actually. And that's the whole point here. That, just going back, regardless of which points you have here and here and here and here, come up with a mechanism that is always giving you that linear model, so this function, the line, that has the lowest possible error. And one way of doing this is called gradient descent. More precisely, batch gradient descent, but that's not so important. Gradient descent. So, and this becomes now, you need to listen and look here very carefully. So we have the generic function for a straight line. It's mx plus b. If we have a single input for one single attribute in your data set, basically only this. And of course, the label. Now, if we have n variables, so here 1, 2, 3, 4, 5, n variables. What's the function for this? How do you model an n-dimensional linear function? What is this looking like if you have not just one x, but x1, x2, x3? Just like this. So that if you have two variables, that would be a plane in a two-dimensional space. You have m1 multiplied by x1 plus m2 multiplied by x2. And so on and so forth. And in the end, plus b. with this function, so, and of course, we want a generic solution for an n-dimensional space, not just for a 1 or 2 dimensional space. So working with this function here is not easy, at least not in the way that we want to do this. So we must make it more simple, and actually where we want to go to, maybe, yeah, I give you 5 minutes to think about how can you get from here to here. What do you have to do to get here? To eventually have actually h of x equals the vector theta, or the matrix, no, well, multiplied by the vector x. You have to change the notation and you have to somehow put it together. I give you 3 or 4 or 5 minutes, talk with your neighbor if you want. Welcome, you're just in time to think about how to come from this function to get to here. First, we change the notation. We replace m with theta. Again, this is just writing it differently. There's no change in the meaning. We replace m with theta, and we replace b with theta. So this becomes theta 1, theta 2, theta j, theta n. And we write b as a theta 0. So the notation becomes this. And we move b or theta 0 to the front. So our new hypothesis, and we write h of x as h theta of x, just to make clear that h depends on both x and theta. So theta 0 plus theta 1 x1 plus theta 2 x2 and so on. In the next step, we make it more compact. So we just write it as a sum notation. We can write everything from here to here as the weighted sum of theta j and xj. We still keep theta 0. And if we now define x0 as 1, so it's here, if we define an x0 as 1, we can write this formula here as this. And if we just have the sum of theta j times xj, we can write it as this, yeah, as vectors. Now we have our linear model, originally notated as this, in a vector notation. And that will allow us a much better and easier calculation. So that's the important, the red part here, that's the important part you must remember. So our original data set D becomes now something like this. This is given, yeah, it's given in the data set x11. But when we make our prediction for this, sorry, this is all given, and yeah, here our goal is now to find theta and have the theta basically in the data. I have all of this. If you multiply and add this, you want to get y as the output. Here's our new, that's b. From the linear model, that's our b. We just put it in front of it. So our goal is to find, we cannot change anything about x. X is given in the data. What we can change and modify and find is theta. So our goal now becomes to find the vector theta for each parameter, theta 1 to n, so that when we calculate this, we get y. If we somehow find here the right theta, here the right theta, here the right theta, here the right theta, then the weighted sum of all of this will be this, or at least close to this. It's important to keep in mind that all these thetas are the same. Now we want to find one theta 0, one theta 1, one theta j, so that for all the instances in your data set, you have reasonably good predictions for y. Is that clear? That's our goal, to find theta. We want to weight. Theta is just a weight. It's a parameter. So when we talk about linear regression, we call it typically a parameter, but it's nothing else but a weight for your input. Theta 1 is a weight for your given input x1 in the data set. Theta j is a weight for your given input xj in your data set. And that's the solution. That's, yeah. Yeah. Entschuldigung? That's the same. Theta is m. And the question is, what is it? We need to find this. Yeah. So theta here is m, and theta 0 is b in your linear two-dimensional model. And the big question is, what is it? How can we find it? What's the specific numbers so that you can make your predictions? And this is the answer. That's the gradient descent algorithm. It's very simple. It works very, very well. This is like a key cornerstone or milestone in machine learning. It's linear regression, as you see later, it's limited. Right? It's a linear model. It cannot do what ChatGPT is doing, or not even close. But gradient descent is a technique that is being used in most state-of-the-art machine learning algorithms. It's used in most neural networks. We talked about that in one of the last lectures in this lecture series. So we get back to gradient descent in probably 6 weeks or 8 weeks from now. It's very simple. It's very effective. So what we do is we initialize theta randomly with very small numbers. And then we continue this step here until the stopping criteria is met. The stopping criteria is met means that you're happy with the outcome, that your error is 0, which basically never happens. So, or the error is small enough, whatever you consider as small enough, or maybe the error is not improving anymore over a given amount of time, or maybe you're limited by computing time and you say, my homework is due tomorrow, I only have 6 hours left. And your stopping criteria is just continue this for 6 hours, whatever the result is after 6 hours, or 6 minutes, or whatever. So what we do is for each, so that's the vector theta with your weights. And for each element in theta, so theta j, we take the given randomly chosen theta j, take the old value and subtract the small, it's called a learning rate, so it's just a small constant, multiplied by the sum of the errors multiplied by the attribute you are looking at. So you are looking, let's say, at one student. You have one attribute given, either the study time or the average marks. And for this one variable, you make the prediction. You take a given student. You make a prediction for that student. You look how good the prediction is. That's the error. And you multiply this error with the variable you are currently looking at. So you do this for each variable. Xj and theta. So this theta j is the weight for this x. After that, you go to the next theta. Keep in mind that the error is just the difference between your prediction and your actual target, and the prediction is just this, what we had on the previous slides. Theta 0 plus all of this. I show you how this works in a simple example. Sorry for this cough. It's really since 1 month, I think. It's not infectious anymore, but still there. So you have a given data set. That is your given data set. Just one variable x1 and your given label y. Now, this is, well, like I did this toy example. So I created a theta 0 and a theta 1. These are the values, but you would never know this. This is what you want to find. I just used that. So if you can see it, 0.5 multiplied by 1 plus 1.5 multiplied by 1 is 0.5 plus 1.5 is 2. 0.5 times 1 plus 1.5 times 2 equals 3.5. But you do not know this. You only have this in your data, x1 and y. So all you know is and what you always do, like when you start the process, is you define your you define your x0 as 1. That was in one of the previous slides. So you know that the input of your function is 1 and 1. Here, 1 and 1, and the output should be 2. If the input to your function is 1 and 2, so here, 1 and 2, the output should be 3.5. If your input is 1 and 4, the output should be 6.5. That's all given here. If your input is 4, so the x0 is not plotted here. This is your original data. So if your input is 4, your output should be 6.5. And now we have a new unknown x1, that is 3, and the question is, what's y? So this is the actual, but like I showed to you before, this is the actual but unknown function. And this is now how gradient descent works. That's the formula here that I just showed to you, and we apply this. So in the first step, let me have a quick look. You initialize theta randomly. So we initialize theta 0 randomly with a small number. We initialize theta 1 randomly with a small number. We make our prediction. So 0.02 multiplied by 1 plus 0.01 multiplied by 1 equals 0.03. So the error is 1.97 or minus 1.97. Doesn't really matter. And we do that for all instances. And you see you have quite large errors. And now you calculate this. So yeah, that's what we just had. That's the error. You multiply this error by x0. So x0 is always 1. So that's always here the same as this. And for x1, you again multiply the error by x1. So for the first instance, it remains minus 1.97. And here, 2 multiplied by 3.46 is minus 6.92. And you sum up all the errors. So the sum is this and this. And if you now put all these numbers in this formula, you get the old theta j, so theta 0 is here, minus the learning rate is given. It's a small number that you just choose. Here, the learning rate is given here, multiplied by the sum of the errors. And you get this new value for the new theta 0. And you get this new value for theta 1. If you now use, so you see here, theta 0, we had 0.02. Now we use the new value here and here. If you plot this data, the first randomly chosen function was this one. Your new function, this one here, actually, that's the new function. 0.15 plus 0.39 x1. You get this linear model, iteration 1. And you can see already it has improved. And if you continue this, so first iteration, second iteration, that was on the previous slides, the next iteration, the next iteration, the next iteration, or actually iteration 100. With iteration 100, you have a near perfect solution. You probably never will have like an exactly perfect solution that depends on the learning rate. You will always like jump a little bit. But I mean, that's as close as anyone would want to get. And this works for any dimension, for any amount of data. So you can use this if you want to make simple predictions where you assume a linear relationship. It's relatively fast. It's easy to implement. Yeah, I think you will do that in the lab session. But yeah, I mean, you can do this in Excel, implement this in Excel. And in Python, it's just a few lines of code. Yeah. So now you know that this formula works. But the big question is, why does it work? And how did the original inventors came up with the formula? I mean, this is not a formula that just pops up in your head, right? It's very simple, but I think if you look at this, there must be some steps before that, before you get to this formula. So how do you get there? And this is what we are looking at. So let's start all over from the beginning. We know what we want to have. We want our linear model. We want to minimize the overall error. So that's like given. We have given an error. It's just the difference between the prediction and the actual value. And we have to have this as low as possible. We call this a cost function. The costs of this algorithm are defined by the amount of error, and we want to have the costs, the error, as low as possible. So our cost function is the sum of all the individual errors, and we want to minimize it based, like with respect to theta. Theta is given, that's the only thing we can change. For all the instances 1 to m in the data set. Now, for linear regression, we have a special cost function. That's what the student mentioned before. We take the squared error. We will see later why that is very important. So intuitively, what we want to optimize is just the sum of all the errors. But for linear regression and for gradient descent, we will optimize the sum of the squared errors. And we actually take half of it. That just makes calculations easier later. Typically in practice, you use 1 divided by m or 1 divided by 2m. So, and this is nothing else but this. This is what we want to optimize. The square of the difference between the prediction and the actual value. In the exam, so there's many variations in the literature. In the exam, please remember and use this formula. Okay, but we will not do this exercise now. I'll just show you something. So that you see again, yeah? Where? This one?
No. Yes, this one, the big one. Below. And yes, in this line, and in the equation for J, the legal equation, the big equation, this one. Yeah. Yeah. But it should be I superscript I. Or the same notation.
Which one do you
Here? Yeah.
This should be E superscript I.
Because we live in the instance.
Yes, yeah, that's right. This I, the I would be here. No, let me. Yes, you are right. But it's for all the instances. Yeah. I didn't put the I up, because it's already squared. Yeah.
Well spotted. First students who saw that in giving these lectures in 7 years, so good, thank you. Okay, let's look at what happens if we vary theta. We vary, so to make it simple, we take theta 0 equals 0, so we can ignore it. We only vary theta 1. We take 0, 0.5, 1, 1.5, 2, and 2.5. Based on this theta, you obviously get a different y hat. Here are the functions plotted. So if theta 1 equals 0, you get this line. If theta 1 equals 0.5, you get this line, and so on. If you now look at this at home in more detail, but here you get this error, you get this error, you get this error, and so on. Now, if you look at the cost function that I just provided to you, the squared error, you get a chart like this. You see already, okay, just going back, you see already here, the error is lowest here. So of all the given thetas, theta 1.5 is the best because the overall error is lowest. If you square the error, you will get a chart like this. That is your cost function chart. Based on what theta you choose, this is your error, your squared sum of errors. So imagine we start here, and then we find a way to update theta. We get here, here, here. That's the optimal theta. Actually, it would be even better to go a little bit more to the right side. Probably the real minimum would be at, I don't know, 1.56 or something. And what you see here, this is a convex function. What does that mean? Going basically back.
So
Yeah.
does not have local minimum like a convex monomial and
Yeah. No, you're shooting above the. I want a more simple answer. So, what do we want? We want the lowest error, right? We want to find that theta that gives us the lowest error. But we start with a random theta. We randomly, for instance, start here. But we have, we can plug in here all kinds of thetas and come up with a smooth function. How do we know? So we want to find this point, or actually this point. How can we do that mathematically? Just shout out.
slope of the cost function for
Yeah.
ascending, and it on which side of the middle.
Yeah, we wanted. Yeah.
The minimum slope should be.
So what do we want to find? Which point? What's the slope? Exactly. We want to find that point on this curve where the slope is 0. Here, that's the minima of the function. How do we do that? Yeah. Yeah. Right. So okay, first again the main idea. That's given. We start with some random parameters and we iteratively modify theta to find the minimum. So it could be we start here, we get there, we jump here, we continue to modify. Maybe we see it's still not 0, we continue, we see now it's bigger, and we go back. In a 2-dimensional space, or actually a 3-dimensional space, it would look like this. So if the most simple linear model always has 2 variables, theta 0 and theta 1. The data set maybe has just 1 variable, that's the most simple case. But then the model, to model this 1 variable in the data set, would have 2 variables, m and b, or theta 0 and theta 1. So theta 0 and theta 1. And based on how we choose this, the error would look like this, and we want to find the minima here. Of course, just so that you're not confused, these numbers could differ. I mean, the minimum of a given cost function is not always where theta 0 is 0 and theta 1 is 0. This could be any value. I mean, that's the big question that we want to find. Which theta 1 and which theta 0 gives us here the minimum value. So we must know, should we increase? So once we have our first iteration, we must know, do we want to increase or decrease theta, each of the thetas? How much to increase or decrease them, and when to stop. And that's what we just said. We need to basically find the slope. Or to do that, we calculate the gradient. The gradient tells us the direction, first of all, in which we should go to increase or decrease the costs. And the gradient is also larger if we are far away from the minimum, and it's smaller when we are closer to the minimum. That means, and it's very, very useful. So just going back here, the gradient will be relatively large. So we can make a big update. We can maybe jump here, or let's say here. Here the gradient is already almost zero. It's very small. So we can use this information to decide, okay, then let's just make a small update. Let's not try out this value next, but if we are here, let's just try as the next value, maybe here. That's also implied here. The first step, here's a large gradient, so you do a big update, and then the steps become smaller and smaller and smaller. Maybe you remember this from high school or from some math classes, the gradient of a multivariable function, and that's what we are having, a multivariable function. We have x1, x2, x3, and so on. And that's a vector of all the function's partial derivatives. So if you want the gradient of our cost function, you must build the partial derivatives of all the individual functions. And you can look at that at home if you are not familiar with this anymore. Just again, so if you want to build the gradient from this, you take the derivative of this function and of this function. For now, in this lecture series, we only look at very simple examples where you have a global minimum with linear regression. There's only one minimum with a given cost function. If you continue with machine learning, you will find cost functions where you have different minima, like a local minima here and here, where you believe maybe, oh, I'm finished, I'm done. This is as good as it gets, because if you continue the learning, increase the error. But actually, if you would continue varying your parameter, you might end up finding a better solution. Now, so this is the maybe more intuitive updates. So this is what I showed to you before, and I showed you it's working. That's the gradient descent formula that you can easily calculate. The intuition is this formula. You want to modify each theta j so that it contributes to the overall error becoming as low as possible. So for each theta j, you want to modify it based on the gradient of the cost function. So what you do is you take at a given point the gradient of the cost function. The gradient tells you in which direction to go, minus or plus, and how much. And you just subtract that from your given theta. And because the gradient can be relatively large, you just have your learning rate that is scaling it down. If you look at this, the gradient here is, so if you go, okay, let's start here, 0. If you go 1 unit to the right, you go basically from 60 to 10. So the grade, so basically the derivative here would be 50 or minus 50. That's of course, you do not want to update theta by 50. If you start with theta equaling 0, you do not want to try theta 50. That would be way out of this. You want to update it by 0.1 or 0.5. So therefore, you need a small scaling factor here. But this is the important part. At the given theta, you calculate the gradient of the cost function, so of the error function. So how do you get from here to here? And maybe that's a good time for a break. It's a bit early for a break, but you can use this break and think about this and talk with your colleagues. How can you get there? I would say 10 minutes. Or do you want to continue? I just show you the solution and we continue. Who wants a break? No one. Okay, good. We continue. I just show you the solution. All right. So we cannot calculate with this, right? Going back here. This is nothing where you can just say, oh, let's build the derivative from this. So let's try to make this more specific. The cost function was given as this. The difference between prediction and actual target and squared multiplied by 1.5. So we want to have the derivative of this. Maybe you remember that the derivative of a sum is the same as the sum of the derivatives of the individual parts. So we can, okay, before we get to that, first, again, we cannot really calculate with this, so we replace this with our hypothesis, h of x, 0. And we ignore this for now. We can look at this later. The important part is here, the derivative. Right, and that's, so we ignore the sum as well because we plug in that later. Because like I said, the sum, the derivative of a sum is the same as the sum of the derivatives. Okay, let me look. Now we have this little problem here with the square. So we apply the chain rule to this inner term, which brings this term here to the outside, like the 2 gets here, and then the inside term is here, and the outside part remains like this, but we lose the square. And now we substitute this here, this function, by the actual values, or well, not real numbers, but you remember, this is our hypothesis, and it's calculated as θ0 plus θ1 multiplied by x1, and so on. Sorry, it's not this one, like this part here. This part we substitute with this. And now, oops, we really can build the derivative of this. What's the derivative, the partial derivative of this expression with respect to θ j? If you build the derivative of this expression with respect to θ j. Yeah. Yeah. Why? Yeah. Yeah, exactly. So it looks complicated on first glance, but yeah, only here we have θ j, and if you build the everything else we can ignore. If you build the derivative of this, xj remains. So here, xj remains, and this term is just what we had here. Yeah, and that's basically it. We put back the sum. So yeah, here we put in the sum again. This here is nothing else but the error. Now that's the prediction, that is y hat. Y hat minus y is the error. This remains here, and this we didn't touch. So this is something, like I showed you before, that you can just apply, you can just calculate it very easily. And this is the intuition. gradient descent. We take the gradient to decrease the error. So now again, just the formula: initialize theta randomly and update all the elements in theta until your stopping criteria is met. With intuitively this formula, but with this formula you cannot calculate, so you use this formula. And that's it. That's gradient descent. There's a few assumptions behind linear regression. First one is your data is linear. And of course, most data in real life is not linear. If you look at pretty much any data, you will never have the perfect linear model for this. But very often in businesses, if you have a simple customer data, you can get reasonably good results with this. So we kind of need a second assumption to make this assumption true. And the second assumption is just, if you build a linear model and you do not get a perfect solution, the reason for this is noise. So you could argue that actually your linear model, or the true model, would be your linear model that we just had, plus some noise, and the noise is normal distributed. But that's not so important for this lecture. And another assumption, but it's also not so important now, that the independent variables are not highly correlated with each other. What is important is how to measure the performance. This is also important for the exam, that you know the differences of these things. When we talk about machine learning, and at least in particular linear regression, we have different ways of expressing performance. We have the cost function. That's what we just talked about in this lecture all the time. That is the sum of the squared errors. And the cost function is used to find and optimize your linear model. It must be squared, because only then you can build the gradient, build the derivative and find the gradient. If you would not have the squared, then this would be just linear as well. You can't optimize only this model. You have, at least not with gradient descent, you couldn't do that. Now, and then we have other performance measures. Let's say they are more for humans. This is for the machine learning model. As a human, you are not so much interested in this error. You are more interested in the mean absolute error. That is what everyone intuitively would consider the metric to measure the overall average error. You just take the average of all the errors. So you look at each instance in your data set, each student, calculate the prediction compared with the actual value, calculate for each student how far off you are from your actual value, sum it all up, and build the average. And if you tell some other person, even your grandmother, I did something, a machine learning model, that can predict a student's salary, and the average error is 10,000, or I can build something that can predict how much money you will get for your house, and the average error is 12,000, you have a good idea of what that means. Everyone has a good idea of what that means. There's a second metric frequently being used for regression. So all of this is regression. Yeah, of course, for classification, you cannot calculate these metrics. There's a second metric. It's called root mean square error, RMSE. And that is the square of the errors divided, so it's the average squared error, and the square root out of this. Why would anyone use this? Do you find that intuitive? Would you tell your grandmother the root mean square error is this? Do you think she would say, oh yeah, I know what that means?
I get you listen to it, have estimate of resilience.
Why do you?
My guess is that we do the square to have value with the same value units as
The same units as the variables. I think that will not be the case here, right? Well, at least I don't think that's the case. Machine learning. Maybe think about that. But any other ideas?
Because errors can be positive and negative as well.
Someone's talking online. That's very good. I appreciate that. Can you repeat?
Because errors can be positive and negative as well.
Because errors can be positive and negative as well. No, that's not really the reason. That's, I mean, here you, of course, that's indeed an important point. Errors can be negative and positive, so you should not just sum them up, because then they could cancel out in some cases. So for the mean absolute error, you also take the absolute values. I didn't say that, so thank you for this comment. But if you take the absolute values, then it doesn't matter if the errors are positive or negative. So that's not the reason really here. Yeah, that is probably the main reason, that larger errors for individual instances have a bigger effect on your overall error. Now, this is not maybe always wanted. That's really depending on the application scenario. Do you want to penalize larger errors stronger? So let's assume you have two instances, and in one scenario, you have for both instances an error of 2. Then you would get the same result here and here. But let's imagine another scenario where you have for one instance an error of 0, and for the other one an error of 4. The mean absolute error would be the same. The normal average error is 2. But if you square it here, then you would have 16. You would have 16 here divided by 2. It's 8. Square root of 8 is larger than 2. Right, yeah. Was haben wir dann? I'm not sure. As far as I know, the main reason for root mean square errors indeed just to penalize larger differences stronger, if you want that in your application scenario. So there's no right or wrong answer. I mean, what is better? Having for every user a small error, or just for a few users large errors, for the other users very good predictions? I don't know. Yeah, I mean, so very often in research papers you will find both metrics to be reported. Yeah, yeah, that was, oh, we are too quick. Let's see, maybe we continue a little bit. That was your first real machine learning algorithm. So where real learning is involved. Learning in terms of you have an incremental approach that is giving you a model in the end. That is what I would consider real learning. That's how humans work as well. You learn every day a little bit, and then some model forms up in your brain how the world works. And linear regression, I think I don't have that on the slides, but of course, what's the advantage of linear regression compared to KNN, what we learned last lecture? Yeah. Yeah, But what's the advantage there? So let's assume it is not that generally linear regression gives you better predictions than KNN. Sometimes KNN works better, sometimes linear regression works better. But in general, what's very nice about linear regression? You are computer scientists, or some of you are computer scientists. The other ones are still some technical subjects, mechatronics or something. So if you think about better between algorithms, you should always think about memory run. Of course, first of all, you should think about performance in terms of root mean square error or mean absolute error. But you cannot say one of the two algorithms is always better. So then the next important things are runtime, memory, complexity. What about memory and runtime, especially runtime of linear regression? Well, at least once you have your model, linear regression is extremely fast. You just take the weighted sum of your inputs. That's milliseconds to do. And also, it doesn't matter how large your data set is. You can have, once you have your model, you can have a gigantic data set. It doesn't matter. You just take your one instance you want to make a prediction for and put it into your formula. And let's say you have 100 attributes to model a student. I mean, doing 100 times the multiplication and then summing it up, that's like nothing for a computer. That's really the fraction of a millisecond, probably. If you use KNN, for every prediction, you must have all your data in memory. And then you must calculate all the distances between your input instance and all the other ones. So if you have 1 million instances in your data set for KNN, and you want to make a prediction for one instance, for one student, you must do 1 million times a distance calculation in a 100-dimensional space, the Euclidean distance. I mean, that's roughly said 1 million times more expensive than linear regression. Then you need a lot of memory. You remember in the KNN lecture, I told you, at least on a normal computer, as long as you don't have any special optimizations, you will probably run into memory problems once you have 100,000 or 1 million instances. So that's the nice thing about linear regression. There's many variations of linear regression, also about gradient descent. You now had the example of batch gradient descent. In batch gradient descent, you use the entire data set. That's what I showed you. There's variations such as stochastic and mini-batch gradient descent. In stochastic gradient descent, you just look at one instance and update the parameters, go to the next instance, update the parameters, go to the next instance, and so on. Now, batch gradient descent has the problem that for large data sets, the training takes a very long time. Imagine you have a large data set, 10 million instances, and then you must go through all data all the time. And then mini batch gradient descent is just a mix between the two. So you define a batch size, let's say 100, and you update your parameters after 100, with the first 100 instances and then the next 100 instances. For gradient descent, for linear regression, there's also a much simpler solution. It's called the normal equation or closed form solution. So actually, instead of using gradient descent, there's a formula. I don't have it on the slides. There's a formula that allows you to just calculate the model perfectly. So you don't need this iterative process. And for small instances, this works also quite well. But for more larger data sets, gradient descent is more suitable. And as I said, gradient descent is the major milestone for machine learning. You will need that later for neural networks as well. So linear regression is a very nice example to show you gradient descent. There's many extensions to linear regression. There's polynomial regression, where you then indeed don't have a linear model, but a polynomial model. It helps you to model more complex data, but it's also prone to overfitting. We talk about that in the next lecture, what overfitting means. Yeah. In some final words, if you work in the lab sessions with scikit-learn or some other libraries, you very often are required to have this train set, like your variables, and then this extra data set or your vector with the labels. Any questions about this? We have lots of time left, so yeah.
We are ready to our formula of the descent, starting with changing the cost. The cost function is the difference between our prediction to the data and square. So it can be y minus y hat squared or y hat minus y squared. If I inverse it, I will arrive at formula for the gradient descent with the opposite side of the sum, right?
So you basically mean here, if you change this, should be the same. If let's say this is 10 and this is 3, then this way you arrive at 7. If you change it, 3 minus 10 is minus 7. But if you square it, you get 49. Right? Or am I misunderstanding?
I was thinking about computation.
Some other point here in the formula.
Now,
Okay, good. Any other questions? Yeah. Yeah. Good question. So about alpha, the learning rate. And if you choose it too large, you will always jump above the optimum. Yeah, you will always jump here and then back there and back here and back there. If you choose it too small, the updates will be just tiny, so that it will take a long time to get to the optimum. Of course, if you have enough computing power, it's probably better to rather choose a small alpha and you just let it run longer, because then you will be more likely to achieve a good solution. But ideally you choose the optimal alpha, but what that is, no one can tell you. That's also a hyperparameter. Remember in K and N, I mentioned this. K is a hyperparameter. There's no way of coming up with a very smart solution that is telling you the optimal hyperparameter, the optimal K for K and N. Same about the learning rate. There's just some gut feeling or rule of thumbs about these numbers. Most machine learning libraries have some defaults because these numbers typically work well, but there's no guarantee for it. So yeah, you can try out, like if you get very weird results, maybe try out a different learning rate. Like if you see that the error is jumping, something like this, and it's not improving, chances are your learning rate is too high. Or if you see the error is just slowly improving, maybe your learning rate is too low. Good. I think, I mean, we could, but it's really a bit early. I think we should continue a little bit. Let me see what's the next lecture, if this makes sense to do. Yeah, it makes sense to do. But we have a break, 10 minutes until 10:05. It's 12 minutes. 10:05. Then we continue. I will prepare the next lecture. Or you know what? You want to continue or want to go home? Raise your hand if you want to continue. If you like this lecture, raise your hand if you want to go home. We continue next time. No one. Yeah, you are the lazy ones. I remember your face. No. Okay, but we continue. 10 minutes, like I said, 10:05, and then we continue.